Good morning all from the modular shed, where I want to test these 6 supercapacitors which I have now put in series with little link wires, and more specifically I want to test the opto-isolators, which are sort of integrated into these protection boards and then bust together with this pair of wires across all 6 supercapacitors, so that we can see whether the opto transistors on the sort of far side of the optos are conducting. So what I've done is I've soldered 2 wires onto these buses and put them into this meter, which is set to ohms. So at the moment it's saying that the resistance, it's not quite right to say that a transistor has resistance because it depends on many factors, but anyway, this is measuring the resistance of these transistor junctions as greater than about, I can't remember, 40 megohms or something. So the fact is, neither one of these 6 opto transistors is switched on and conducting, they're all switched off. Now this is an OR gate effectively. If either transistor turns on, it'll pull the, again, resistance between these 2 wires down to a low value. So the only way we're going to be able to achieve that is to charge up a capacitor, get the protection circuit to come on, and watch this resistance fall. Now this voltage is simply the measurement between yellow and green, so we're measuring the voltage on this cap. I have previously charged all these caps, so they're sitting at a sort of mid voltage. This power supply is going to put out 0.5 amp, so I'm going to switch that on, and we're in constant voltage mode. No, that's constant current mode, sorry, and it is putting out exactly 0.5 amp. The capacitor will now charge up to 2.5 volts, not very quickly, but I don't want to overwhelm the protection circuit when it does kick in. So to spare you the waiting, I will now, in the edit, switch this to high speed, and I'll come back when we're a bit nearer 2.5 volts. I'm actually going to change the lighting now because I want to see when these blue LEDs come on, and they will come on when their forward voltage is reached. Now that starts at about 2.2 volts, I think, but it's incredibly dim. At about 2.4 volts you can see them, so I'm going to go to the higher up lights. Oh, that makes the DMMs more difficult to see, doesn't it? That I didn't consider. What can I try? Try moving this whole thing forward a bit. But I do want to be able to see the current on this power supply. And tip these down a bit. Yeah, that's better. No, I can't see this blue LED yet at 2.2 volts. Maybe it's more like 2.3 volts. The tiniest faint glow from that blue LED at 2.3 volts. That should be much more visible as we get closer to 2.5. Instead, if you're wondering why I started on this capacitor, it's just because the wires coming from my voltmeter happen to sort of come out these 2 points. I might do the middle 2 first, and then if it's still interesting, move on to the outer ones. But what I'm particularly interested in is when this protection circuit turns on, do I see the effect of that? Do I see that action take place via the opto transistors, collector and emitter legs? Let's see if we can see the glow of that LED. I'll just turn the lights off completely. Yes, you can see the blue glow of that LED at 2.3.5 volts or thereabouts. Lights back on. Incidentally, the little marking on these crop clips is an S, and I've written S on the ones like there where I've soldered them, because they're so much better if you solder them. The yellow one I haven't soldered yet, it's still just crimped in, and the connections can be really terrible. So it's definitely good to slide these covers back, solder the wire, I cut it back a bit, solder it onto the crop clip, slide the cover back on, and you'll have much less trouble with these cheapy croc clip wires. So 2.475 volts, still not seeing any resistance across the collector emitter junction of the opto transistor, even at 2.48 volts on the capacitor. The blue LED is now quite easily visible. When is this thing going to respond? Ah, there it goes. So we saw what, 12k briefly, I think. We're down now to 5k ohms. Oh, sudden drop to 1k ohms. That might be because this thing changed ranges. 1.5k. So what I'm going to do now is leave this for a while to kind of pump as much energy into the capacitor as possible, saturate it as much as possible, and see how low this drops. But certainly we can see that the opto is now flagging up that the protection circuit has come on. So this is the point at which the opto would trigger my high current power supply, which will be somewhere between 5 and 10 amps to shut down, and just leave the low current power supply, about half an amp, to continue charging, and that will be when it's charging all 6 capacitors in series. Continue charging the capacitors. This one has reached top, it's reached its maximum voltage, the protection circuit is on, offsetting this half an amp, just burning it up in that transistor, and then all the other capacitors can come up to meet this one. That's how the system's intended to work. We're now down below 1k, but I'll leave it for a bit, see how low that goes. Well, okay, I don't think it's going to go much lower. We might get that down to 800 ohms, possibly by just waiting, but little point. So let's turn this off. Now that voltage should fall away, and this resistance across collector and emitter on the opto will start to rise eventually very quickly. 6k, 7k, 8k, 11k, 14k, 20k, 100k, some megs, and it's gone off. So the next thing I want to do is move the measuring to the next capacitor. Let's measure this one. Move the power supply connection, so that's at 1.4 volts. That's what I'm doing very well. I'll put the power supply connections close to the cap, not that it makes a huge amount of difference. This is essentially a 4-wire measurement because there's precious little current in the measuring wires. I think I've got a problem with these wires, you know. It's probably the yellow one, because the green one does have an S on it. I have soldered that. I soldered the red and black wires as well, so it must be this yellow wire. Yeah, dodgy. Right, anyway, let's switch that on. 500 milliamps. Up goes the capacitor voltage, and once again I'm going to wait till it gets to 2.5 volts and hope to see, this one's still got its blue light on, by the way, because, well, it's still charged, above the forward voltage of that LED. That LED incidentally is connected directly across the capacitor terminals with no resistor. Doesn't need one, because until you get to about 3 volts, you're not really burning significant current in that LED. And this capacitor tops out at 2.5 volts. So it's a safe thing to do, to just strap it straight across. Right, I'll shut up now and we'll watch that go up to 2.5 and hope that this opto also goes to a low resistance, or at least the collector emitter junction of this transistor starts to conduct, and we'll see that on that meter. So 2.4 volts on the capacitor that we're charging. This one, the blue LED, is now visible. You'll probably have noticed that I was playing with higher currents because it was taking a long time to charge. I'm at an amp at the moment. Yeah, waiting for that to get up to 2.5. The protection circuit to switch on. The opto-isolator to have infrared LED light up and put light onto the optical base, effectively, of the opto transistor, and some current to start flowing through that collector emitter junction, and for that to show up on my DVM as a resistance. Keep bringing this current down as we get close to the point where the protection circuit will switch on. And there it goes. 50k, 45k, 10k ohms, that is, cross collector emitter. Now on this opto, this one will be megohms again. All of them are megohms except this one, which is allowing a current to flow between these two bus wires. 1.8k. Yeah, it changes a bit when the range changes, because it might change the voltage that it puts across these 2 points, which it then uses to get a current to flow. It measures the current and then calculates a resistance. Interesting. Interesting to watch the voltage across these 2 wires to see what happens to it when this changes its range. Right, we're getting down to the 1k ohms, which I noticed that, well, on this DMM, it might show up differently on different DMMs because they may use a different voltage. This has a 4-volt lithium battery in it, so I don't know what voltage it puts across these two, but it might be different in a DMM that uses a 9-volt battery. That blue LED is quite bright now at 2.546 volts across the capacitor. Oh, that's I've got quite a lot of current going through it. Let's take that down to 500 milliamps. That's going to climb up momentarily as this voltage falls a little bit. But once again, it's about 1k that we get to when the capacitor is completely charged. So I now know that the middle 2 capacitors and specifically the opto-isolator circuits are working. Let's just test all the others now. Now checking capacitor number 2. Now, interestingly, the opto on this one is still conducting as the voltage on this falls away. So although I'm charging capacitor number 2, we're actually seeing a current flow showing up as a resistance on opto number 4. That's going to go away soon as this gets up to the maximum resistance that this meter can measure, which is some number of megohms. 1 megohm to 19 megohms. And that's it. This one, number 2, is now coming up. 1.6 volts. Let's go into speed up. Right, that's what I wanted to see, is a reduction in the resistance here. That means that current is flowing through opto number 2. I'll wait till that gets down to about 1k ohms. I'd like them all to be similar in terms of the resistance that shows up on here. In other words, the amount of conductivity there is across that junction. I'll wait till that gets down to 1K and then I'll test capacitor number 1. Good, there's the 1K ohms I was looking for. Shut the power supply off and move these connections to another capacitor. There we go, 2 amps into capacitor number 1. The opto on capacitor, oh, which one is it? 2, I suppose, that's got the brightest LED, is gradually turning off. Let's get some current into cap 1, see if its opto works. I think what I'll do on this one is I'll leave this on 1 amp and I'll only turn it down, my finger's on the down button, when I see the opto transistor start to conduct. This of course is the opto transistor on supercap number 1. Now, I think these protection circuits can take 1 amp. We could test that actually. I could get my thermal imaging camera, could do it perhaps on one of these where it's easier to see, and just see how hot that transistor gets at different currents. That could be quite fun. Still not got a reaction on here, even at 2.48 volts. I think that one didn't happen until over 2.5, did it? There it goes, current comes down to 0.5 amp. Oh, that's dropped back out again because that's fallen back. Well, that's fine. I'll let that recover at 0.5 amp. And that should switch back on again. I'll go into fast again. Actually, this raises an interesting point. If the opto turns on and switches off a very high current power supply, will we get a sort of oscillation? Because the cap voltage will fall back, this will go out of conduction, it's gone into conduction again now. So will you get a trembling, an oscillation at the point where this gets up to the threshold of switching on the protection circuit? Or will there be enough hysteresis in the system somewhere to prevent that happening? Well, we won't know until I get these optos connected up to the 2 power supplies, the high current and the low current, and see what actually takes place. Right, just waiting for the 1K on there now. Then I'll test these 2 caps, and then I might do this thermal imaging thing, just to keep you watching, because 2 more capacitors, me doing exactly the same thing as I've done on 4 capacitors so far, it's not terribly interesting, is it? Yeah, just waiting for this to go under 1K, which I'm kind of using as a benchmark for all of these. If you're wondering why I keep pressing the lights on and off on the meters, they keep beeping because they're going to go into timeout, and that's an easy way to reset the timeout. There is a way to get these to stay on permanently, but it means you've got to hold a button. I suppose I could do it. Turn it off, hold a button like mode, turn it on. Doesn't tell you that it's going to stay on now, but apparently that's what it does. Let's do this one. Hold a button, turn it on, put the light on. They should stay on now. Come on, go under 1K. I'm bored with waiting. Right, that'll do. So turn that one off, and I'll rehook the wires up for cap 5, and I'll go and get the thermal imaging camera. Right, I'm going to leave that at 1 amp on the power supply. We're at 2.5 volts and 4K. That will continue to come down. Now let's power up this thing and see if we can get some temperature measurements from... Now these resistors barely get warm at all. All the heat seems to be dissipated in the transistor. So let's see if we can see that. Yeah, so you can see on the upper corner, where am I? There, on the, oh, you can't see that very well. On the upper corner of the board, that's the transistor there, and that's where its tab is soldered onto the circuit board. These three resistors, which would be down here, just don't get warm at all. Right, we're looking for the max temperature, so 40 degrees is the max temperature. Sorry about the reflection of my light, perhaps I'll do that. Yeah, so max is 43 degrees now, and you can see it's showing the max up there where the red marker is. 45 degrees now. I'm not too concerned with that below about 60 degrees. I suppose would be fine. 50 degrees now is the max on that transistor. So I guess this circuit can offset 1 amp. Still climbing though, 54 degrees, 55 degrees. Hearing a strange noise, but it might just be something outside. I don't know. Right, I'm going to lower that to 0.5 amp now. Oh, I know what it is. It's the clicking of the shutter on this thing. Yeah, that's what it is. So that's down at 0.5 amp now, and we'll just watch this thing cool down. It will take a while to cool down. How's the battery? It's pretty good. So that's creeping up. Did that go under a K? You may have noticed 2.527 battery voltage. So I'm just watching that coming down. No, it is coming down. Yeah, 51 degrees. We'll see where it gets to in steady state. I'll go into speeded up mode. Well, it seems to have settled at about 45 degrees. It's quite difficult to hold this thing. So now I'll go into speeded up mode, wait till that gets to 1K, and then we'll just recheck the temperature of the transistor. You can just about make out the three resistors, but they're not even yellow, red, they're certainly not white. So they're just not giving out any heat at all. I'll come back when that gets to 1K. Right, Cat5 has got down to my benchmark resistance across the opto-transistor collector emitter junction. It was going a bit slow, so I pushed this up to 530 milliamps just to push it on a bit because I was getting bored. Right, I'm going to switch to Cap6 and do it pretty much all in speed up. You can watch it if you want, but you don't have to. Right, that's it. Capacitor 6 has reached its, or at least Opto 6 has reached its target of 1 k ohm. That means some current is flowing through the collector emitter junction of the opto transistor. So I'm done. I've charged all 6 capacitors up. I've checked that all 6 optos are working and conducting when the protection circuit is on. So yeah, I think that's all I wanted to do. Next step will be putting this panel onto a baseboard, getting my power supplies fixed down onto that, and also the amplifier, and putting the speakers somewhere, because of course the idea of this is that it's a supercapacitor powered Bluetooth speaker project. But today, from the modular shed, cheerio.